So welcome to Math341, lecture 8, 9, 8, something like that. What we're going to do today is we're going to talk about independence. We're going to talk about the inclusion-exclusion principle. We did a little bit about that at the end of the last class. We will talk a little bit about proofs by induction. We will talk a little bit about multinomial coefficients. Is there anybody here who brought a legal ID to campus today and is willing to volunteer? Okay, excellent. Not yet, but I will need it later. Okay, so the first thing is independence. So we have some idea of when two events are independent. Can somebody give me, just like in words, what it would mean for two events to be independent? Yes?
The outcome of one does not affect the outcome of
Good, the outcome of one doesn't affect the outcome of another. Knowledge of one doesn't give you knowledge of the other. When I'm rolling two die, if I want a sum of 7, and I know the first die is 3 and they're fair, I have no additional information. If I want a sum of 2, and the first die is a 3, I have complete information now as to what my probability is. So let's think about what we have. So right now we have things such as the probability of A given B, and this was the probability of A intersect B divided by the probability of B. What do you think should be true if A and B are independent? What do you think this should equal? I'm sorry? Not 0.
probability of A.
It should be the probability of A. What's the probability of A given that B happens? Well, if B gives you no information about A, then the probability that this happens, this should just be, if independent, the probability of A. So the question becomes, how do we want to define formally independence? We could do something like this and say, two events are independent if the probability of A given, well, but this is now making one of the events special relative to the other. So there's a more symmetric way to write this. We can write this as the probability of A and B, A intersect B, is the probability of A times the probability of B. This is a much better launching point. Why is this better? I don't have to worry about division by 0. Also, A and B are now appearing symmetrically. So this will be our definition for two events. All right? So two events will be independent if the probability of A and B is the probability of A times the probability of B. So there's often, the standard problems, you might have seen them in high school. So-and-so has this many shirts and this many pants and this many sneakers. How many outfits can they have? What's the probability of various things? And each one can be viewed independently of the others. We're assuming that there is no fashion constraints that you would never wear this shirt with those pants. This is basically my advising my daughter what to wear as opposed to my wife advising my daughter on what to wear. All right. What if we have three events? Do you think it should be the probability of A intersect B intersect C is the probability of A, probability of B, probability of C? Do you think that this would be a good definition of independence? So I'm seeing some yeses and I'm seeing some no's. Yes?
Well, that could be true without each pair of events being independent.
Right, so this could be true without having A and B be independent. So if A, B, and C are all independent, I would expect A and B to also be independent. So this is not enough. And I believe the book goes through an example where you can have this is true, but they're not pairwise independent. So you can come up with examples. If not, it's a good idea for you to try to find an example. Find three events where this is true, but pairwise it's not true. What might you want to choose for the probability of C? What would be a good extreme case to choose for the probability of C? 0. Because then both sides will be 0, and then you have tremendous freedom with A and B. So this is not enough. We also need the probability of A intersect B is the probability of A, probability of B. Probability of A intersect C is the probability of A, probability of C. This is so much fun to write. Probability of B intersect C is the probability of B, probability of C. If we had 4 events, it would be any subset is independent, and just proceed by induction. So you would want the probability of A intersect B intersect C intersect D is the product of the probabilities. And then for any 3 of them, they're independent. And then any 2 of them, they're independent. And it just keeps going on and on and on like this. Okay? So when events are independent, it's very easy to calculate the probability that 2 things happen. It's just the product of the probabilities. So whenever possible, we want to concentrate on events that are easy to calculate. For a lot of things, it's sometimes easy to calculate the probability something does not happen. Well, if I know the probability that something doesn't happen, then the probability it does happen is just 1 minus that. Okay. Any questions on independence? We're all good on this. Okay, so what we're going to do now is we're going to go to the inclusion-exclusion principle, and we're going to talk about how to calculate more involved things. I think last class we did a little bit of this, and I talked about bridge, where everybody might have all cards in the same suit. So I want to talk about 2 different ones now. So this will be inclusion-exclusion. And so the idea behind inclusion-exclusion is you want to calculate the probability of a union. The probability that at least one of a couple of events happens. Unions are terrible. Unions are very hard to calculate. Intersections are easy. So the idea is you replace a union with a bunch of intersections with various weights. And so the problem I used last time I taught was, imagine you have a bunch of dots, and these represent some kind of network. And I want to connect things. You want to make sure that every node can talk to every other node, right? It would be really bad if you had something that was isolated and, I can't access this website. How can you make sure that everybody can talk to everybody? I don't care how efficient it is. Give me a way that guarantees everybody talks to everybody.
You just draw edges from each node to every other node?
Yeah, you do the, well, that's a little bit easy to draw for me. You just do the really expensive, connect everybody to everybody. This is called the complete graph. It's horrible in terms of cost, but it works. And then the question becomes, well, can I do something with less? So here's an example that would work. This is the spoken hub model. This is how airlines work. What's bad about this model? Yes?
If anything happens to the center.
Yeah, if anything happens to the center, then all of a sudden you cannot communicate with anyone. So think of this as the Panama Canal is closed or the Suez Canal is closed. All of a sudden it's going to be very bad. Okay? So when you are looking at your graph networks, you might be very concerned about making sure that you don't have key points where if they fail, the whole system goes down. Sometimes people like to do what's called a bipartite graph. So they have things on the left, things on the right, and you can't connect 2 things on the left, you can't connect 2 things on the right. And what you might do is you might look at connections. And you might have a rule, you can't connect 2 things to the same thing. Well, let's put down, let's start by saying we can't connect 2 things to the same thing. So we'll start off like this. This is great that you can communicate with one of your neighbors, but you can't communicate anywhere else. Now we'll do another set. So this is, say, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we connected 1 with 1, 2 with 2, 3 with 3, 4 with 4, 5 with 5. Let's choose another permutation. So I did 1, 2, 3, 4, 5, going to 1, 2, 3, 4, 5. I could choose another permutation. Maybe I choose 5, 4, 3, 2, 1. And so now 5 goes to 1, 4 goes to 2, 3 goes to 3, 2 goes to 4, and 1 goes to 5. Now everybody can talk to everybody, but I've got this extra edge here that I don't really need. It was a little bit wasteful. It's not really adding anything. So what you might want to do is you might want to be connecting something like this where you make sure you never connect something to itself or its opposite again. On the first connection, you might as well assume 1 goes to 1, 2 goes to 2, because they have to go somewhere. Yes?
But wouldn't 1 only be able to talk to 1, 5, or 1 on the other side, or 5 on the other side?
Well, let's see. Okay, so at this point, we may not be. You're
would
right.
be able to
So at
talk
this
to
point,
3.
1 can talk to 1, to 5, and to this 5. You're right. At this point, we can't talk to everything. You're absolutely correct. I apologize. 2 can talk to 2, 4, and 4, and 3 can only talk to 3. So at this point, we have 3 isolated networks. And then if we put down maybe another thing, if I connected 1 and 2, and I connected 3 and 4, maybe 3 and 4, something like that, then that would work. So I'd have to connect maybe 1 with a 2 over there, and 3 with a 4 over here. And so the idea is, how do I place things in such a way? I want to make sure I don't connect a number with a number. So when I'm choosing my permutations, it comes down to what's the probability if I choose a permutation, I don't have a number that's fixed. And so if you have, I always get it is a derangement, I believe, is when you do not have any numbers that are fixed. So derangement, so no number fixed. So we want to calculate what's the probability of a derangement. I will give just one more example of inclusion-exclusion. This is a number theory example. It's one of the only things that both I and my wife, who's a professor of marketing, both use. So there's such a thing called twin primes, where p and p plus 2 are both prime. So these are called twin primes. It is unknown if there are infinitely many twin primes. Only in the past few years have we finally been able to show that there are infinitely many primes differing by a bounded amount. The original bounded amount was 70 million. It was such a monumental breakthrough, you never try to get the best value. The fact that you got anything finite was better than anything that had been done before. Now I think the best value is below 1,000. People for years studied the sum where p is a twin prime of the sum of 1 over p. If this sum were infinite, what would it mean if that sum were infinite? What must be true if it's infinite? So what would be true if the sum is infinite? What can you deduce about the twin primes? There are infinitely many of them. If there are only finitely many twin primes, the sum has to be finite. Unfortunately, using inclusion-exclusion, one was able to prove in the early 1900s that the sum is finite. That means there could be infinitely many primes, or there could not. Infinitely many twin primes or not. Years ago, I think in the 1980s, Nicely was trying to calculate the value of this constant, and he was using a new Pentium computer. And so it had, the Intel processor. They used to call their processors by numbers: the 286, the 386, the 486. And then Intel launched a huge campaign. The most important part of your computer is the processor. This is the new Pentium chip. Intel actually knew that there was an issue with the Pentium chip. It had trouble with divisions. Not often, and not enormously. But if you are doing billions and trillions of consecutive divisions, there will be small mistakes. But how many people need to do billions and trillions of consecutive divisions? It's very rare to have a situation like that. Well, when Nicely was trying to calculate the twin prime constant using his new Pentium chip, it wasn't matching the results on the old 486. And this became a huge catastrophe for Intel, costing them, I believe, hundreds of millions of dollars. Their advertisers rushed out with commercials. We agree with Intel that the processor is the most important part of the computer. Ours can divide. And you then have all these people in a panic calling up Intel asking for a replacement processor. And again, for most people, if you're doing Excel spreadsheets for businesses, you are not going to be doing a billion consecutive divisions where you need 9 digits accuracy. But this mistake in Intel's chip was discovered by a mathematical result using inclusion-exclusion. So sometimes these results are wonderful as ways of just testing what's out there. This is one of the best applications. So what I want to do is I want to do inclusion-exclusion. We did a little bit of it with bridge hands, but carefully for the probability of a derangement. So what I want is we have
We
rearrange 1, 2, n, probability no number is unmoved. So if we did 1, 2, 3, 4, 4, 1, 2, 3, that would be good. If we did 1, 2, 3, 4, 4, 2, 1, 3, that would be bad. So is everybody clear? I want to know what is the probability if I reorder my numbers that every number is moved to a different spot. So how many ways can I order n numbers? Not n minus 1. N squared. I'm sorry? N factorial. I have n numbers. There's n ways to choose which numbers first, n minus 1 ways to then choose which number is second. So there are n factorial permutations. And we want to calculate how many of these permutations leave a number unmoved. So let's let AI be the event that I is fixed, so it doesn't move. So we want to calculate the probability of A1 union A2 union AN. This would be the probability at least one number is fixed. And if we can calculate the probability that at least one number is fixed, then the probability that no number is fixed is just 1 minus that. So we want to calculate the probability of this union. Well, this is terrible. Maybe just the number 1 is fixed, or maybe the numbers 3 and 7 are fixed. Or maybe 1, 2, 7, 11, 14, 17 are fixed. There are so many different ways to do this. This is why we want to use inclusion-exclusion. We want to look at simple events. So A, I1, I2, Ik equals the event that I1, I2, Ik are all fixed. And when I write things, I will always assume my indices are different values. I'll never write down something like A11. Right? There's really no need to calculate A11. A11 is the simple event A1. Right? And then A1, 1, 2, 2, 3 is just A1, 2, 3. So these events are much easier to calculate. And the idea is by calculating these events, we can then calculate the more complicated union event. All right, so let's start doing the calculation of these simpler basic events. All right, so let's calculate. Does everybody agree the probability of A1 equals the probability of AN? It doesn't really matter which one I look at. Fixing the first is the same as fixing the second. All right, how many ways are there to rearrange n numbers where the first number is fixed? I'm sorry?
first number's fixed?
The first number is fixed. So 1 goes to 1. And then 2, 3 to n, I can do whatever the hell I want. Not n minus 1, n minus 1 factorial. So the first number is fixed. And then I have n minus 1 factorial ways to change around everything else. And then what do I divide this by? N factorial. Can you simplify this? Sure. I don't know if it's worth simplifying, but I will just write the simplification for now. This is the same as 1 over n. It might be worth noting that, it might not. It comes down to how the algebra goes. Okay. So note there are n such events, or n choose 1 such events. that I do know I want to write that way. Now, let's look at the probability of A12 with the probability of A13 equals all the way up to the probability of A(n minus 1n. How many ways are there to rearrange the numbers so that the first two, say, are fixed? N minus 2 factorial over n factorial. So this is going to be 1 over n minus 1. So how many ways are there for these events? N choose 2. So there are n choose 2 such events. Okay? So hopefully the pattern is clear at this point as to what happens. So the probability of the union would be the sum of the singletons. Well, how many singletons do we have? We have n choose 1 singletons, and each one of these is 1 over n. Then we subtract the doubletons. N choose 2 doubletons, and each one is 1 over n minus 1. Then we add the triples, 1 over n minus 1, n minus 2, and so on and so on and so on. Actually, the next one would be a minus sign. And we'll go through in a few minutes and explain, why this really does count everything. Imagine I have something that occurs exactly 3 times. But we'll do this as an aside now. Say you have some x which is in A1, which is in the union. And say it's in exactly 3 of the A's. So if it's in 3 of the A's, how many times do we count it here? We count it 3 times. How many times do we count it over here? Why 3 times? So it's got to, if we're choosing 2 things, and it's got to be in both of them, right? Because it's intersections. So we would have 3 times as well. And then for the last one, how many times would we count it? We would count it once. And so the net effect is that if it's in all of them, yes?
Could you explain that way again, please?
Sure. So let's look at an x that's in A1 through AN exactly 3 times. So when we have our stuff going on here, let me go a little bit further down on the board. So let's say we have A1 union AN. And then what we're going to be doing is we have, on this side, we have A1, we'll have the union of the AI. And then we'll subtract off the union of the AIJ. And then we'll add back the union of the AIJK. And so on and so on and so on. This is the inclusion-exclusion. I'm trying to keep track of how many times something occurs. If it occurs exactly 3 times, I count it here once, because it's in the union. In these over here, how many times is it counted? It's counted 3 times. How many times is it counted here? Let's say it's in the sets A1, A2, A3. I get it in A12, in A13, and A23. So I would also get it 3 times. So that would be my minus 3. And then here, the only time I would have it would be in A123, which would be a plus 1. So if you occur in exactly 3 of them, then you see I've counted it once over here, and the net count over here is also 1. If you did it 4 times, then you would have to add back now, or subtract back, union AIJKL. So now it's in exactly 3 of them. Well, can it ever be in an IJKL? If it's only in exactly 3 of them, no. Right? If you're only in 3 of them, can you ever be in an I, J, K, L? No. So all of these ones from here onward won't matter. Now let's say that you were in 4 of them. So if you're in 4 of them, now it would have A1, 2, A1, 3, A1, 4, A2, 3, A2, 4, and A3, 4. That'd be 6. Now I want to look at how many ways it could be in 3 of them. I could have A1, 2, 3, A1, 2, 4, A1, 3, 4, and A2, 3, 4. And then I could have it in A1, 2, 3, 4. 4 minus 6 plus 4 minus 1 is 1. So if it's in exactly 4 of them, it's going to come out as being counted just once. Yes?
Does that mean like n choose 1 minus n choose 2?
Yeah, so what we'll do now is we'll prove it in general. Do you agree that if it doesn't occur in the union, it doesn't occur at all on this side? So I only have to worry about things that occur exactly k times. So let's assume it occurs k times. So we'll say x is in here, and it's in exactly k of the a's. Okay? Then in the first one, how many of the a's will it be in? It'll be in k choose 1 or k in the first one, right? How many pairs will it be? And if it's in exactly k of them, I have to choose 2 of those indices. So I would then subtract off k choose 2. Then I would add in k choose 3, subtract off k choose 4, all the way down to -1 to k choose k. And so it'll be, I think, -1 to the k minus 1 power. So this would count, if it's in exactly k of them, how many times it's in the intersections. Well, what I'm going to do now is I'm going to subtract 1 and then add 1. And I can write -1 as negative k choose 0. And this now becomes just negative k choose 0 minus k choose 1 plus k choose 2 minus ... plus -1 to the k choose k plus 1. But by the binomial theorem, this is just -1 minus 1 to the k plus 1. Well, what's 1 minus 1 to the k? Just 0. So this is the probability, this is the combinatorial proof that we have counted it exactly once. It turns out it's a lot easier to count something multiple times with signs and weights. We'll count it k times here, and k choose 2 times here, and k choose 3 times here, and k choose 4 times there. And at the end of the day, it's counted just once if it's in our sets, and 0 times if it's not in our sets. Yes?
Can you explain why we can't just go directly from both binomials to 1 minus 1?
This is the binomial theorem.
Okay.
X plus y to the k is the sum, L goes from 0 to k, of k choose L, x to the L, y to the k minus L. This is the binomial theorem. And then we're just using the binomial theorem with x equals 1 and y equals -1. So we will see the binomial theorem many times. Any other questions? How many of you have not seen a proof of the binomial theorem? All right. There are proofs in the book. We will talk about that at some other point. If there's time at the end of class today, I will talk a little bit more about the proof of the binomial theorem. You should have hopefully seen this in calculus when you're taking the derivative of the function x to the n, x plus h to the n, and use the binomial theorem to expand it. Okay, let's go back to the inclusion-exclusion argument. So we now have our formula like this. So the probability of the union was n choose 1, 1 over n, minus n choose 2, 1 over n, n minus 1, plus n choose 3, 1 over n, n minus 1, n minus 2, and so on and so on and so on. Well, what's n choose 1? It's just n. So the first term becomes 1. N choose 2 is n minus 1 over 2. So this is just 1 over 2. But actually, it's not 1 over 2. It's 1 over 2 factorial. The next one is n minus 1, n minus 2 over 3 factorial. And we stop.
Should be plus.
I'm sorry. This one should be a plus, and then this one should be a minus. And then the last term is negative 1, and we divide by n factorial. And so here, let's see, here was 1, and we had a positive sign, so I think it's n minus 1. So this is the probability that at least one number is fixed. So if we looked at 1 minus the probability, we would get 1 minus this. We get 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus dot dot plus negative 1 to the n 1 over n factorial. Okay, and if you remember, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 dot. This is converging to what number? So what number is this converging to?
E.
Not e. So it can't be, wait, no, nobody's speaking. Why can't it be e? No. Why can't it be e? E is larger than 1. This is a probability. You know it can't be e. But it's close to e. It is 1 over e. It's e to the negative 1. I should really write this as 1 over 1 factorial if you want. And this is 1 over 0 factorial. Yes?
Are the signs, you switch from the top row to this row?
Yes, because I'm doing 1 minus. So then anything that was a positive becomes a minus, anything that was a minus becomes a positive. This converges to 1 over e. We will see that number many times this semester. 1 over e turns out to be the probability of a lot of very interesting events. So this is telling you that if you have a very large number of numbers and you rearrange them, and all the arrangements are equally likely, the probability that at least one number is fixed, at least one number doesn't move, is 1 over e. This means it's quite likely that at least one number will be fixed. But you do have a good chance of having nothing fixed. Okay. Any other questions on this? So this is inclusion-exclusion. The idea is intersections are typically easier events to calculate than unions. And you represent a union in terms of intersections, and you just play this game. So the book goes through a lot of the calculations for, a bridge hand where at least one person has all cards in one suit. Is anybody from either of these states? Anybody from either state? Okay, good. I chose well. Let's rearrange the letters and look at how many distinct words we can form. And I do not care if these are English words. So I will consider Iowa a word. How many ways can I rearrange the letters of Iowa? 4 factorial. Mississippi is a lot more complicated. Why is Mississippi harder? A lot of repetitions. So what we're going to do is we're going to add some labels and then forget about them. First S, second S, third S, fourth S. Now we have 4 distinct S's. First I, second I, third I, fourth I, first P, second P, And just because I'm having so much fun, first M. How many ways can I now rearrange the letters of Mississippi? 11 factorial. But because some of these letters are equivalent, when you rearrange them, how many ways can I rearrange the 4 S's? So I get to divide this by 4 factorial. How many ways can I rearrange the 4 I's? 4 factorial. How many ways can I rearrange the 2 P's? And then a 1 factorial for the M. And not surprisingly, the sum of the numbers here, 4, 4, 2, 1, equals 11. You could view this as 4 factorial over 1 factorial, 1 factorial, 1 factorial, 1 factorial. For those of you who love bad math expressions, this is not quite as bad as the complex conjugate of C divided by C. Right? But this is kind of painful to read. So we will typically not write all the 1 factorials down there. How many of you have not seen multinomial coefficients? Okay. So I know some people have taken stats classes and seen stuff like this. We will write this as 11, 4, 4, 2, 1. And note, of course, this is also the same as 11, 4, 2, 4, 1. Right? It doesn't matter the order in which we write them. Yes?
I'm curious with Mississippi. Why can't we just pronounce words that sound a little funny with 2 S's and 2 I's and 2 P's? Why do we care about S1, S2, S3, S4?
Well, because so we don't want to count MISS different from MISS, where in this one I kept the S's in their normal position, and in this one I switched them. When I look at all the different ways to write letters, because these S's are the same, I want to be very careful that I don't count the same thing twice. I can't distinguish the S's.
Did you approach this the same way as you did some of the card drawings in the book with like blank, choose blank, and then you multiply those?
It's similar. I mean, what we're basically doing is we're looking at all the ways we can write things. If everything is distinct, if everything is different from everything else, then there's no problem. The difficulty is when we have letters that are the same. How can you tell the difference if I give you the word Ohio from H-I-O-O and H-I-O-O? And in the first case, I do the first O followed by the second O, and in the second case, I do the second O followed by the first O. I don't want to count these as 2 different words. If all the letters are distinct, then I have no problem. But with Mississippi, because I have letters in common, I have an issue. And so the simplest way to remove this issue is you add labels. And then we're going to remove the labels. This is very similar to how many ways are there to choose k people from n when order doesn't matter. First choose when order matters, and then remove the ordering by dividing by k factorial. Similarly over here, I'll remove the ordering. If I choose a word, I've got a special order of the S's, I've got a special order of the I's, I've got a special order of the P's. Okay. So if I give you n choose k, this is really n choose k, n minus k, if I want to write this with a multinomial coefficient. And what this tells you is that I can relate multinomials and binomials. It all comes down to how you want to do the algebra. So for example, let's say I give you x plus y to the n. This is the binomial theorem. It's the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus k. I could look at x plus y plus z to the n. And this should now be like a double sum. The sum k goes from 0 to n, the sum L goes from 0 to how large could L get to? It'll go up to n minus k. And then I'll have a sum j goes from 0 to n minus k minus L. N k L j, x to the k, y to the L, z to the j. Because I can't have my sum of k plus L plus j greater than n. So once I've chosen a value of k, I can't have L go beyond n minus k, or k plus L will be too large. Once I have k and L, j can go at most. Now, if you don't want to worry about this, what does 4 choose 5? How many ways can you choose 5 people from 4? 0. This is supposed to be 4 factorial over 5 factorial negative 1 factorial. What does this tell you about negative 1 factorial? I'm sorry? What does negative 1 factorial have to be?
Infinity?
Yes. Well, it could actually be negative infinity as well, but it's going to be of size infinity. And so the binomial coefficient is actually interpreted this way. That if you are dividing by a negative factorial, that's supposed to be an infinity. And have we talked about the gamma function briefly? When you do the gamma function, it actually makes sense, and this is where this is coming from. You would have the same thing here. You can have these sums go however you want, and this will just automatically reinterpret itself. Yes?
Where did you introduce the random variables KLJ and why?
Well, just because when I expand this, I'm going to have some number of x's, some number of y's, and some number of z's. Right? Now, over here, we've got to be a little bit careful. So this has to be fixed a little bit. When we expand this, what must be true about k plus j plus L? It has to go. So I have to add the constraint k plus L plus j equals n. So another way around this is to say, well, if k plus L plus j has to equal n, then j is just going to be n minus k minus L. J is no longer free. So I can drop this condition, and I would have my coefficient would be n, k, comma, L, comma, n minus k minus L. And that's the most concise way to do it. If you want, you could even have L go all the way up to n, because it knows to make this 0. It's just a question of how you define things. Now, you can also put in the minus k, that's fine. One way to look at this is by grouping, is x plus y plus z to the n. So we've talked about grouping before. This is one of my favorite techniques. Reduce to what you know. Well, now what theorem can I use to expand this? Binomial. So this would be the sum, say, L goes from 0 to n of x plus y to the L, and then it'll be z to the n minus L. Oh, sorry, I'm missing the binomial coefficient, sorry. So it'll be n choose L, x plus y to the L, z to the n minus L. And now what can I do for x plus y to the L? I could expand that out. So I'll have the sum, maybe L goes from 0 to n, sum m goes from 0 to L, n choose L choose m, and then I'll have x to the m, y to the L minus m, z to the n minus L. And then if you just play with changing variables and whatnot, you can see that these binomial coefficients will somehow have to give you the multinomial coefficient. So you can think of them combinatorially, you can think of them as coming from the binomial coefficients when you expand. There's a lot of different algebra you can do in terms of how you want to phrase things. All right, so I want to end very briefly with proofs by induction. So how many of you have not seen proofs by induction? Right, everybody has seen proofs by induction. So typically you have your base case, you have your inductive step. All right, how many of you have ever seen the proof that everybody has the same name? All right, a couple of you. So you have your ID on you. Please take it out. So statement P of n in any group Does everybody believe you all have the same name? I just do that so I now know one person's name. Let's prove this by induction. Base case. Is P1 true? If you have a group with just one person, is everybody in that group similarly named? So now, inductive step. Assume Pn, show Pn plus 1 follows. Alright? I am not known for my artwork. And then we'll end with like somebody doing disco. Okay. 1, 2, 3, and n plus 1. What can you tell me must be true about the first n people? Same name. What can you tell me about the last n people? Same name. And since 2 is in both groups, everybody has the same name. Did you realize your name was so popular?
Wow, I did.
What's wrong with this proof? For those of you who have not seen this before, what's wrong with this proof?
The assumption's a little heavy.
Where?
So the first person is how you, and then we're assuming every person up to that to n.
Well, P1, P1, the base case is clearly true. Where's the mistake?
The first and the last and people don't necessarily interact.
I'm sorry?
There's not.
Yes. So for instance, if I take n equals 3, so I've got 1, 2, 3, 4 people now, there will be an overlap. But if I take n equals 1, there is not an overlap. That's the issue. So if you want, people often think of induction as a stairway. This is the stairway. Here's n equals 1, here's n equals 2, n equals 3, n equals 4, and so on. So we have the ridiculous situation where from here onward everything is fine, we just can't get there. Do you agree that if in every group of 2 people everybody has the same name, then everybody in the world has the same name? Sure. Because just take one person and then just match them with each person one by one. So it's because we don't have this step, we don't have n equals 1 implies n equals 2, that things fail. You can prove a lot of really great results using this. You can prove every integer is a perfect square. So as a nice exercise for extra credit, modify this argument and prove every positive integer is a perfect square. So yes, you can write 3 as a square. All right. Any other questions? We have about 20 seconds left. So a lot of stuff today. We did inclusion-exclusion, breaking down unions to intersections and just combining them with weights. We did what it means to be independent. We did the binomial theorem. We did multinomial coefficients. So this ends chapter, I think, 1 through 6. We will start the next section on random variables, and then nothing past Friday will be on the midterm. I do not remember exactly what is on the midterm. I write these exams before the semester begins, so I don't know what is on them.